Correct.
The problem with our data set is because we don't have labeled anomalies. With any metrics we have, there's no way to have in the data set that ITM or New Relic provides, they spotted anomalies. So we have to, prior to apply the neural network to recognize the pattern, we have to identify the anomalies. And how we do so, there are, in the literature, there are more than 15 kinds of anomaly detection algorithms. And if you've seen on my screen here, we applied the local outlier factor. The local outlier factor is an algorithm that calculates the density. It's like a density probability between the previous stage of a data point and the current stage of a data point, comparing the neighborhood. So based on this picture I'm depicting here, you have, imagine you have a lot of scattered data points, which represent the state of your server and application features values. And you want, based on that, you want to detect automatically which ones are anomalous based on the data you have. So the way we do, we calculate, it does a Gaussian distribution between all the data points and compare that with the neighborhood. And if the density calculated is far from the others, it detects this feature as an anomaly in a specific time. And we use this label to feed our neural network with the timestamp that an anomaly occurred and the value of the metric. Prior to apply a neural network to intelligently identify the norm and the pattern, we have to identify the anomaly points, the anomalous points, because there's no way to identify that on the data set. In our model, we have two approaches, an unsupervised approach for detecting the anomaly with the local outlier factor, and the supervised approach using the labeled local outlier factor data for applying the pattern recognition. Imagine the X points here, the X1 and X2, they represent an anomaly. So they are far from the green ones and also the cluster with the yellow ones. That's a very simple and good example that how an anomaly behaves. Based on the values of X1 and X2, when you calculate the density of all the data points, it turns out they are very far from the other ones. And that's how we detect anomaly. And the right side here, we have an example of one of the metrics we captured from the application, the ShopZ application. This is the other transaction call counts. It represents count counts based on access of the users. And if you see here, well, in the 14th of September, you have the rise peak. And all the yellow points here represented how the local outlier factor algorithm detected those anomalies. And it gives me the value of the metric and when it occurred. And if you go to the end of the graph, you see a lot of yellow points that also represents anomalies. But if you compare with the 14th of September, you don't see a rise in the peak, right? But why does it detect as an anomaly? If you compare the window here, it was stable most of the time. And then started reaching values that was very different from this window frame here. So that the algorithm detects and calculates the density and spot those as anomalies as well. And how to reduce the error in those cases, comparing the other metrics. If in the other metrics that we analyze with the same time frame, all of them are already anomalies as though this one is an anomaly.